Hi everybody! We are nearing the end of our derivatives unit. We are on the way to knowing how to take the derivative of all the things. Today we are going to talk about exponential and logarithmic functions. We're also going to note, as I do every year, that I'm pretty sure this is Mike Huckabee on this guy's laptop. Former presidential candidate, Mike Huckabee. He was not successful. You may not even remember who he is. Okay, so we're going to talk about derivatives of exponential and logs today. And you may be saying, Ms. Britton, you already told us how to do the derivative of the exponential function e to the x. And that is true. That is true. But once again, I didn't tell you the whole truth. So that's the first thing we have to talk about today. What a dirty liar I am. Okay, ready? This will be fun. Okay, so here's what you know so far, right? First, I told you that the derivative of e to the x was itself e to the x. Then I said, oh, by the way, there's this thing called the chain rule, and if there's something up there in a cloud or in a U or whatever you want to call it, then you have to take the derivative of that as well. So when we learned the chain rule, we graduated from being able to just take the derivative of an e to the x to being able to take the derivative of an e to any cloud, because I know all I have to do is chain rule. So for example, if you have something like y equals e to the negative 3x, this becomes dy dx equals that thing, and then we chain rule the derivative of the cloud. So this would be times negative 3. Over here, I'm going to use different notation. I have e to the cloud. Doesn't matter what's up here. We just chain rule it, right? So it's still, because it's an e to the cloud, going to be an e to that cloud. It always stays the same. And then we multiply by the derivative of the cloud. Right? This is old news. We need to add a layer to this today. And here's the layer. E is a special case. E is the natural base, right? And so as long as you're taking the derivative of an exponential function with the base of e, the natural base, you don't have to worry about the piece I didn't tell you about. And here's the real truth. We can take the derivative of an exponential function with any base. It doesn't have to be an e to the x. It could be a 2 to the x, or a 7 to the x, or a pi to the x. It could be any base. And the derivative doesn't really change that much. There's just one little adjustment. A change of base, if you will, if you remember those rules from Algebra 2. It doesn't matter what the base is. Look at this rule. Remember, a is just a number. Remember, if you're dealing with an exponential function, you're going to have a numerical base, and you're going to have an x expression as your exponent. If you don't have a numerical base, it's not an exponential function. Okay, so remember, if you have something like x to the third, that's a power rule. If you have 3 to the x, that's where we're going to apply this rule. You have a numerical base and a variable in your exponent. If you have a variable in your base and a variable in your exponent, this rule does not apply. We will talk about this in our next video. Okay, so when you are about to apply this rule, the most important thing that you need to make sure of is that you are applying the right rule to the right type of function. So an exponential function would be anything where, anything where this base is a number, and then up here is where your x is. Notice the rule hasn't changed much. The derivative of a to the u has an a to the u and a chain rule chunk. The only thing that changed is I got this new piece here, the ln of a. In other words, the natural log of my new base. So if your base is something other than e, you're going to follow the same rule, and you're going to tack on an ln of the base. It's a change of base. Okay. Now you guys have fancy calculators now that you can put in a log or an exponential in any base, but back in the day we didn't have that. We only had natural and base 10, and so we had to do change of base formula in our calculators. Okay. Now you may be thinking, how has every derivative I've ever done not been wrong if you didn't tell me this part? But remember, since e is the natural base, When I do this to a base e, what I'm adding in, or what I'm tacking on here, is an ln of e. And the ln of e is 1. So it's kind of like chain ruling a sine x. Right? Well, you can write times 1 if you want to, but you don't need to. So this is the whole truth. Right? Before, we were just kind of inching along with that special case. All right, so little added layer. Let's take a look at a couple of these. All right, so if I have y equals 3 to the 2x, again, numerical base and a function up here, I need 3 chunks to my derivative. The first thing I'm going to do is literally just rewrite it as it is. That's the first piece of every exponential derivative. It's the original guy. Bring it down. Then I have to have 2 things. I need the ln of the base, and I need a chain rule piece. Whichever one you feel like you're going to forget, do that one first. Right? There's no rule because it's multiplications. It doesn't really matter which one you do first. Okay, so I'm going to say, okay, that's 3 to the 2x. There's a cloud, so I better chain rule, so times 2. Once I'm done chain ruling, oh, by the way, ln of 3, right? The ln in my base. And now I'm done. Okay. It is important to remember, this may seem silly that I'm saying this, but it is important to remember that the natural log of 3 is nothing but a number. As Aaliyah would say, ln ain't nothing but a number. You guys remember that? Remember that song? So I'm going to put it out front, 2 ln of e, and then I'm going to say 3, whoa, to the 2x, right? I say that because in the event that they ask you to take a second derivative or something, I'm surprised at how often people ask me, well, what am I supposed to do with that ln? Or they try to take the derivative of it, which we're going to talk about next. It's just a constant. The ln of 3 is a number. If you put it into your calculator, you get a number, right? It's the number that if you raised e to, you would get a 3. That's what it is. So treat it like a number. All right, how about this one? It says 4 to the sine x. So again, I have a numerical base, and then I have an expression for x up here. So that is an exponential function. I'm going to use my rule. So again, the first thing I'm going to do is write down the original function. I'm going to chain rule. The derivative of sine is cosine. And then I can't forget the natural log of my base, ln of 4. You can bet AP is going to have a choice here, right, where there's no ln of 4. Right? But that's it. And again, you can rewrite the ln of 4 out front. You can rewrite this in any way you want, but it really doesn't matter because it's just a product. All right, so the log function. As you may remember from your days of Algebra 2, logs and exponentials are inverses of one another, right? Then the log undoes the exponential undoes the log. I know what you're thinking. You're saying, Ms. Brenna, I don't remember the rules of logs at all. If you don't remember the rules of logs, you're going to want to review those. They're going to become important, and you do have to understand what logarithms are in order to work with them. All right, so if we look at the log function, I always think that the log function looks like a square root function with a tail, right? Because it does look a heck of a lot like a square root function, but we remember that it has this vertical asymptote here. Because if I have, for example, the ln of x, what that's really saying, if I have y equals ln of x, that's saying that if I raise e to the y, I'm going to get x. Right? Did you ever do that? When I taught Algebra 2, I called this the loop-de-loop. I would say, okay, that's a base e, right? So we would say, you can rewrite this log as e to the y equals x. So you can always take a log and translate it into an exponential, and for some reason people find exponentials a lot easier to look at. Right? So the idea is this. I have to have a vertical asymptote here because if I put a 0 in up here, I get a 1. If I put positive numbers in, I get big. And if I put negative numbers in, I get little. Right? So I'm never going to get a 0 out of this. So you can't raise e to the anything and get a 0. That's why the e function, exponential function, has a horizontal asymptote here. Well, this is its inverse. It's going to have a vertical asymptote in that same spot. All right, so if we want to talk about the derivative of a log, you won't be surprised to learn that it's related to the derivative of e to the x. All right. So let's take a look at a couple tangent lines. At 1, 0, so at this point, 1, 0 right here, I zoomed in and I drew a little tangent line for you. If you look closely, you will notice that the slope of that tangent line is 1. So at the point 1, 0, I have a slope of 1. It's not very exciting. Right? So one might say, oh, maybe it's like an e to the x and the slope is the same as the x value. Maybe. Let's zoom in on another point. At the point 4 ln of 4, if we zoom in and we take a look at the tangent line, the slope of that tangent line is 1/4. You see what's going on now? Thought you might. Okay, so here's our rule. If you take the derivative of, notice this is the natural log of some function. This is a cloud, right? Your derivative is going to be 1 over said cloud. And here's your chain rule piece, right? Here's your cloud prime. It's your rule. 1 over, and then dy dx, du dx, cloud prime. This is the rule that helps us. No, it's not. Never mind. I just got ahead of myself. Ignore me. Don't listen to me. Okay, listen to me now. All right, so let's take a couple derivatives, right? The derivative of natural log is just 1 over whatever you've got there. If it's an x, the derivative is 1 over x. Okay? If it's a cloud, then it's 1 over cloud and then d cloud. I want you to notice where the d cloud goes. It doesn't go in the denominator. It gets multiplied. It goes in the numerator, technically. Okay, so here I've got an ln of x, so my y prime is literally just going to be 1 over x, and then my chain rule piece here is just a times 1, so I don't need to worry about it. Again, be careful. This chain rule chunk it doesn't go in the denominator. You'll see it written to the side. Sometimes you'll see this same rule written like this. They just show it as the chain rule piece being popped into the numerator. Algebraically, it's the same thing. But it's really important not to pop it into the denominator. Right? So the derivative of the natural log of x is just 1 over x. Okay, here's one that has a chain rule in it. And you're going to notice that these simplify nicely. So you got to be a little bit careful if you're looking at multiple choice. I have the natural log of a cloud here. So my derivative is going to be 1 over that cloud. And then I need to take the derivative of my cloud. I need to do my chain rule. The derivative of 6x squared is 12x. And so you can see here where I'm going to have simplification. This comes out to 12x over 6x squared. So usually when you have natural logs, notice I took the derivative of a natural log and I end up with a function that isn't a natural log. It seems a little bit too simple to be the derivative of a natural log function. But what you'll notice here is you're going to get lots of cancellation, and this ends up just as 2 over x. So sometimes if you're not in the habit of simplifying, you may notice that the answers look way too simple. That's probably what's happening. You're probably getting some cancellation there because it's very, very common with natural log stuff. Okay. Ooh, this is a good one. All right. Again, I have a cloud. I don't care. The derivative of natural log is the same as it's ever been, right? I'm going to do 1 over x cubed sine 2x, and then I have to chain rule. And again, note that that chain rule is on top. Here in this chain rule, I've got a product, right? So I'm going to do my product rule. So x cubed, derivative of sine is cosine. And then sine, derivative of x cubed is 3x squared. So technically you could have just right off the bat written this whole thing in the numerator. You could leave it like that. It's up to you. I'm feeling sassy, so I'm going to rewrite it. All over x cubed sine 2x. And again, you're going to notice here a little bit of canceling. I have a 3x squared here. I have a 2x cubed. I have an x cubed. So technically, I can take an x squared out. Right? This becomes an x, and this becomes an x. You can factor out and cancel an x squared. So don't be surprised if you see answers that are simpler than yours. We do see a lot of simplification with natural logs. Okay. I probably don't have to tell you that there's more to logs because This is the natural log. So what happens when it's an unnatural log? You probably already have some idea, don't you? Okay. The natural log is a special case, right? Because it's the natural log. So if we have a log that isn't a natural log, in other words, if we have a log with a base other than e, so base 2, base 5, base 10, whatever, then there's going to be an extra piece of the derivative. And it's going to be the ln of the base, just like the exponential function. The only thing you have to remember is where it goes. So here's your rule. If you have a log in a base other than e, here's your 1 over cloud, like always, and your cloud prime. Only thing extra here is your ln of your base. Notice it's in the denominator. The ln of the base goes in the denominator. Then the chain rule goes off to the side or goes into the numerator. But be careful to make sure that you put your natural log of the base in the denominator. I always second guess myself on that. I think because I just feel like it's an easy thing to forget. Okay. So again, if you have the natural log, it's just going to be a special case, right? The natural log is nothing but a log in a base e. We just gave it a special name and its own notation. Right? So if I think of the natural log as a log in a base e, I don't really need a separate rule, right? It's 1 over cloud, natural log of my base, and then du dx, cloud prime. Well, the natural log of e is just 1. Right? So it's not really worth writing. Is it wrong to write it? No. But there it is. Okay, let's do a couple. So these are the tricksters. These right here, when they just write log, just log. Because there's nothing there to say to you, hey, I'm a log in a base other than e, pay attention to me. If they just write log, remember that that is a log in a base 10. And because there's no number, they don't have to write the number. It's implied. It's kind of sneaky. And since there's nothing there to kind of draw your attention to it, that's an easy one to miss. Be careful with that. If it's not ln, it's not a natural log, and that you better be tacking on the ln of your base. Okay, so here's my cloud. And there's my a value. So I'm going to do 1 over my cloud, x to the 4th. I'm going to do the ln of my base right now while I'm still down there in that denominator. And then I need to tack on my derivative. So over here I'll do my 4x cubed. This is a rule worth taking a minute to make sure you've memorized. There's so many places that people get jumbled up here. It's easy to forget the natural log, or it's easy to put it in the wrong place. It's easy to put the derivative down here, or put the derivative, or forget to leave this part and then just only take the derivative. So please make sure that you sit down and take a moment to memorize this rule. And again, notice even if your base is different, you're still going to have some cancellation. This x cubed is going to cancel with 3 of those. We're going to end up with 4 over x ln of 10. And again, worth noting, the ln of 10 is just a number. Right? So this is 4 over the ln of 10 times 1 over x. In other words, this is just a constant. So if you were asked to take the derivative of this, it's not like you need a quotient rule or something. Right? This is just a constant. Pull this out front, and then the derivative of 1 over x is easy. Right? So don't let those natural logs, kind of the introduction of these natural logs, they tend to make things look more difficult than they are. They're just a number. Okay, here's one that's going to need a little bit fun chain ruling. Now again, this one was nice. Anytime there's a base other than 10, there's this number sitting there saying like, you really want to do something about me. And so it's a nice reminder, at least it is for me. All right, so here's my cloud. I'm going to think of that as an x to the 1/2. So I have 1 over my cloud, ln of my base, and then I'm going to chain rule. So put my 1/2 x to the negative 1/2 over here. So algebraically, this is a bit of a fun rewrite. You are definitely going to have simplification, but it looks a little bit different in this case because this x to the 1/2 ends up being a square root. in the denominator, right? So I have 1 over 2 square root of x here. So look what happens. Square root of x and square root of x is just x. So I get 1 over 2x ln of 4. Okay, lots of simplification with these. If you're noticing that your answers aren't matching the answers that you're seeing somewhere, look for simplifications. Anytime there's logs involved, there's always tons of simplifications. Alrighty, one more. Here we go. I've got a base 6 and I've got a product rule. A product rule with a chain rule in it. Remember when chain rule was the only question on the table? Those were good times. All right, so I need the derivative of the log of some cloud, and it's a base 6. So again, 1 over my cloud, e to the 2x cosine of x, ln of my base, ln of 6, and then I'll chain rule. Okay, so here's my cloud prime. So I'm going to have an e to the 2x. Derivative cosine is, let me put that negative out here, negative sine x, plus the cosine of x times e to the 2x times 2. So, again with this simplification, I get a negative e to the 2x sine x. I've got a plus 2e to the 2x cosine x. And in the denominator, I have e to the 2x cosine x ln of 6. So if you leave it as one fraction, minimally, your e to the 2x's, you can factor e to the 2x out of the numerator and completely cancel it out. If you choose to split it into two fractions, there's a lot that could happen here, right? If you split this into two fractions, on the first fraction, this turns into a tangent, and on the second fraction, it just turns into a 2 because the cosines cancel out, so you get a 2 and over ln of 6. So again, lots that can be done with these. I'm happy with this. I'm not trying to make life harder than it has to be. You could argue that one fraction is simpler than breaking it into two fractions, but if you break it into two fractions, things cross out. So I guess that's an argument I don't want to have. All right, so again, these are just two rules that need to go on your derivative rules worksheet. You will notice that it is almost filled out. There's only one more, right? Inverse trig. That's it. And then we're going to know how to do all the derivatives. And then it's going to get really fun. All right, please make sure you note any questions that you have on this, and I will see you soon.